Welcome to this explainer. If you look at Earth from space, it honestly looks like a perfect static marble. But zoom in, and it's actually a massive interconnected engine that is constantly running. Today, we're going to take a macro to micro journey into the very foundations of environmental science. We'll be looking at exactly how our incredible planet functions on a grand scale, and then we'll zoom all the way down to explore how we actually monitor its vital signs.
Here is our roadmap for today. We're starting off with Earth's 4 major systems. Then we'll move right into the core ecological principles, examine the drivers of environmental degradation, and finally wrap things up with monitoring and data analysis. Let's dive in.
Section 1. Earth's 4 major systems. To really grasp environmental science, we first have to set the stage. Our Earth is this complex, perfectly balanced interaction of 4 massive spheres. First up is the atmosphere, the gaseous envelope surrounding the Earth. And here's a pretty wild way to think about it. If the Earth were an apple, the atmosphere would actually be thinner than its skin. Yet this totally invisible dynamic shield provides the air we breathe, it regulates our global temperatures, and it blocks out harsh cosmic radiation. It is, quite literally, the planet's breathable skin. Right beneath that skin is the hydrosphere, which includes all the waters on Earth's surface. We are talking oceans, winding rivers, deep underground aquifers, and massive ice caps. Now, consider this. Water isn't just the universal solvent, it acts as a massive global conveyor belt. It distributes heat all the way from the equator to the poles, completely dictating our global weather patterns.
Supporting all of that moving water is the lithosphere. This is the rigid outer part of the Earth, so the crust and the upper mantle. This is the physical foundation we literally stand on. Without the immense structural integrity and all the rich chemical resources locked inside these rocks and soil, absolutely nothing else could take root.
Finally, we reach the biosphere. This includes all the regions of the surface, atmosphere, and hydrosphere occupied by living organisms. The really crucial takeaway here is that the biosphere acts kind of like the ultimate Russian doll. It doesn't exist in isolation. It sits right at the intersection of the atmosphere, hydrosphere, and lithosphere, relying entirely on the immense stability of those first 3 physical systems to support all life on our planet. Moving right along to Section 2, the core ecological principles. Now, what's really interesting is when we shift our focus from those physical structures we just defined over to the invisible rules that actually run the world. Think of these principles as the active, mechanical steps of a great planetary engine. Step 1 is energy flow, simply the movement of energy through systems. This basically starts with the sun and cascades down through plants to animals. Step 2 is nutrient cycling, which is the movement and continuous exchange of organic and inorganic matter. So energy flows linearly, in a straight line through the system, while nutrients just endlessly recycle within it. Together, they are the twin engines driving every single ecosystem on Earth.
And what happens when that great planetary engine hums along perfectly? We get biodiversity. This is the incredibly complex variety of life thriving within the biosphere. Just think about how a single change, like reintroducing wolves to Yellowstone, can completely reshape an entire landscape, right down to the literal flow of the rivers. Biodiversity isn't just some environmental buzzword. It's the ultimate scientific indicator that Earth's systems are healthy and functioning exactly as they're supposed to.
Section 3. Drivers of environmental degradation.
We have to look objectively at the conflicts that threaten this natural order. By examining the data neutrally, we can really understand the specific forces acting as mechanical disruptions right now. Just look at the stark contrast here. On one side, you have the healthy ecological principle of biodiversity. On the other, the mechanical disruption of habitat loss. When physical spaces in the lithosphere and hydrosphere are bulldozed or significantly altered, the biodiversity within the biosphere is mathematically and directly reduced.
Science identifies 3 primary drivers of this degradation, and they act purely as mechanical disruptions to the systems we've talked about. First, pollution, like excess carbon or plastics, which directly alters the chemical makeup of the atmosphere and hydrosphere. Then, deforestation, which disrupts nutrient cycling by removing the lungs of the system. And finally, habitat loss, which directly subtracts from the biosphere's spatial capacity to actually sustain varied life.
Which brings us to our final section, monitoring and data analysis. Let's pan back out and see how humanity actually responds to all of this from an analytical standpoint. Environmental monitoring allows us to track specific disruptions right back to their source systems. For instance, when we monitor pollution levels, that directly informs us about atmospheric and hydrospheric health.
Tracking deforestation gives us highly precise data on nutrient cycling, and measuring habitat loss gives us the direct math on biodiversity. Data analysis is basically our ultimate diagnostic tool. It links the problem directly back to those foundational systems we mapped out at the very start.
So, we're at a pretty critical junction. We know exactly how the major systems interact, we understand the invisible rules driving them, and we have the hard data tracking the disruptions. The absolute key takeaway from all of this is that the systems are mapped and the data is flowing in. The only question left for us is, what is the monitoring going to show us next, and exactly how will we choose to respond to it?